Okay, we are going to look now at the I element. So let me write it down in here. Well, so we're starting with this. We need the capitals, no, not so like this. The I element, and then I'm gonna say constitutive equations. Okay. So let's do the same thing to be consistent and put an I element over here with in the mechanical domain, just a mass in here, and we have a force that is applied. Yeah, that is in the case on the mechanical side. This one on the electrical domain, we're going to have an inductor. It has an inductance L, and it has a voltage across the sides in here. And on a hydraulic system, I'm just going to look at the piece of pipe in here where you have pressure, on both sides, piece of 1 and piece of 2. So the difference in pressure, we're going to call it P, is equal to piece of 2 minus piece of 1. And you have the mass in here of this on mass of fluid, which is going to have, I'm going to call it big M, just for that. So here's the constitutive laws. I mean, this is the physical system. Now the constitutive law, as you normally have seen this, you know that force is equal mass times acceleration, which is x double dot, right? This immediately demonstrates that this equation is in derivative form. Look at this. Isn't it we put it like d x dot dt, like this, right? And yeah, and that if you define the momentum, like the momentum is m times x dot, the momentum p is m times x dot. What is dp dt? With the rate of change of momentum, this is going to be equal to m times d of x dot, d of x dot dt, d of x dot dt, which, let's just clean it up in here. I just want to make sure that we have nice clean right up in there. So let's just go here. You take the derivative d dt of x dot like this, which is going to become x double dot, which is this. And so dp dt is equal to f. Okay? Now, let's just do this, and then later on we're going to do the block diagrams of this whole thing. This is saying that the voltage in this case is the inductance times the derivative of di dt, like this. We know this, and you can also write that the voltage is this is a second order derivative, which you could also write it that way, is equal to L times t square q dt square, or L times q double dot, like that. See, similar to this form. And we have, like in the case of the mechanical system, also a momentum, which would be let's call it flux linkage on the electrical system, but in this case the momentum is also the electrical momentum. In this case will be L times the current I. And in here you also have that dp dt then is equal to the the dp dt would be B, like that. For this other one, you have that the pressure is equal to the mass big M that I call it, and in this case dq dt. Q is the volume flow rate in meters per second, meters cubic meters per second. And then in here you will have that the pressure is going to be big M, but Q is volume, like Q is the volume dt, like this. So in this case you will have that this will be d square of the volume dt square, which is the same thing as doing this m times you could say b, like this double dot, which has the same form. Again, the momentum in the hydraulic system is going to be L times Q, like this, but the momentum dp hydraulic is going to be equal to the pressure, like this. See, all three energy domains have constitutively the same form. This is what, when bond graphs were discovered, that was the idea, that the laws have the same format, but they mean different things in different energy domains. Now let's do the block diagram. So this is my equation in here, basic equation. This is the final derivative form in here, and then now we're going to do the block diagram. So why don't we say this in here? You see the input to this in here is x double dot, like this, and then in here you have the well, actually the input is x dot, yeah? And then gets differentiated. So let's just move like this, x dot, then gets differentiated by 1 time d dt, like this. This becomes x double dot, and then you multiply this by m, and out of this comes the force. Yeah, this is the block diagram of this. This one here, you have that this is the current here, and then gets differentiated d dt, and then this, of course, it would be I double dot, like that, then gets multiplied by L, and out comes the voltage V. That's the electrical one. This one here, you have that the input is Q, and then this gets differentiated like this, and then multiply by the, I think this was an L, this was M, by M, and out of this is going to come P. So this is the block diagram. Now, how do we represent this with the bond graph model now? The bond graph model here, you have, is of course is an I element in here. I'm just going to do put a little color, put some life into this. And in here, the I element, what is the output of the I element when I write it this way? The output is, of course, is the effort variable. So I'll reverse the colors to make it a little interesting. So this is F in here, and what comes in here is X dot. And in this other case, the I element in this notation in here, we have that the I element is, the output is totally consistent. In this case, the output of this is the voltage, and then in here the input is the current. And let's just do one more for this one over here. The I element is going to be like this, yeah, and of course the output in this particular case is the pressure, and this is Q over here. But if we use it in generalized notation, now we are going to say that, let's just pick up, let's do it in red. The I in this case is going to be E, and this is going to be F. This I over here, E and F. Do you see? The element looks the same, but the units are different. Yeah? So this is the derivative form of the I element. So I would say, I told you that from the beginning this was in derivative form. So the equations of this, in summary, for this element in here, you have that E is equal to the I times df dt. You know that dp dt is equal to E. Consequently, the derivative dp dt is going to be equal to I times df dt. So you see, it ends up with the derivative on the right hand side. This is the constitutive equation for the I element in derivative form. But just like we did with the C element, let's look at the integral form. And perhaps using them, now that I hopefully have convinced you that the variables, the form is the same, the variables change, but the equation format is the same, I am going to take advantage of that and just concentrate on the mechanical system to illustrate this example for you. We had that F is equal to m times dx dot dt, which is the same thing as writing mx double dot like that, right? But if I write it in, you could say, I could write this equation, this in terms of x dot. So if you do that, what you will end up doing is you integrate both sides. This would be the integral of m times dx dot dt like this. And what would you end up with? You will end up that to leave this, move this to the other side, you have 1 over m times the integral of f dt is going to be equal to x dot. Or if you feel more comfortable, we put it on the left hand side. So let's rewrite the equation a little nicer. 1 over m times the integral of f dt. How does this play in the block diagram? And how does it play this in the bond graph model? In the block diagram in here, you're going to have that f in here comes in, gets integrated once, and then this gets multiplied by 1 over m, and out of this comes x dot. This is the block diagram of this in integral form. But now in the bond graph form, how do we write this same thing but now in bond graph form? I would do it, and I'm going to do it on the right hand side here, so that this of course is an I element in here where the output is the flow. See, this is x dot is the output, and then the input, see, the input in here is f. So isn't it true that we generalize the notation in here and we say I is equal like this, and this is of course E, and this is F. So consequently, if I rewrite these equations in generalized form like this one, I'm writing that F is equal to 1 over m times the integral of E dt, and I also write that the dp dt is equal to f. So excuse me, is equal to E. Yeah. So these are the constitutive equations of an I element in integral form. And for both, for the electrical system and for the other one, we'll have that same form. Just so to make you feel comfortable about this, I'm just going to do the I for the electrical system over here. You will have the current over here and the voltage over here. And for this other one, in the I element, you will have here Q, and you will have in here the pressure. So, and that is the I element in integral form. Well, and we have studied also the derivative form, but this is the constitutive law for this element.